Yes, I think we can start slowly. It's, I think, 1:30. And this is the introduction to Julia for HPC. And in this part, I'm going to talk about performant Julia code. But before we start, I think it's loud enough for the participant. Okay, thank you for your feedback. Yeah. So my name is Xin Wu, and Alex and I, we are working at PC2, Paderborn Center for Parallel Computing. And the benefit of using Julia for HPC is its performance, right? Performance is the key feature for HPC, and therefore, we have this session for performant Julia code. And during this session, okay, yeah, take a seat. We haven't really started yet. For this session, we have some example code, and those codes are available along with the slide in the GitLab repository. You can take a look at the code. It's a Jupyter notebook. And actually, I can say this afternoon, we will focus on the performance of this very simple function, fx equals 2 times x. This sounds crazy, right? Who cares about the performance of to calculate the 2 times x? But this is really key to understand the performance of the Julia code and also understand the so-called multiple dispatch and so on. Very basic, but very key concepts in Julia. So let's get started. Now we really formally start. So this afternoon, there are 3 topics. The first topic is to show you Julia code is fast. Why Julia code is fast? Just trust us, and we are going to show you some real benchmarks to convince you that Julia code is really fast as optimized C code or Fortran code if you are a guy of Fortran. And then we will talk about Julia compilation by going through the compilation pipeline of Julia. This sounds a little bit advanced, but yeah, no worries. It's not really very low level, and this part is for you to have an understanding about the Julia compilation procedure. So I will just go through it, and for you just have a very high level overview, and then that's it. And last part is about static compilation, right? Right now, you are writing Julia code like a script, for example, Python script or whatever. Is it possible to get the executable, let's say, standard executable like what you will have for C code or Fortran code? This is possible and still in active development. So basically, those are the 3 topics I'm going to talk in the next 1 hour. So first topic first, Julia code is fast. Actually, the performance is a key feature of Julia from the very beginning. Let's look at the benchmark for Julia 0.6. And yeah, I'm a scientist, so therefore I'm always citing scientific paper. This is a key paper published, I'm not sure, 6-7 years ago. This is a milestone paper for the Julia development by the core developers from Julia. In this paper, they benchmarked the performance of Julia code with respect to, for the online participants, with this virtual laser pointer, with respect to JavaScript, Python script, or whatever, and then to compare the performance of the Julia code with respect to the C code as a baseline. So basically, if the performance of the Julia code is along this line, this vertical line, this means Julia code is as fast as C code, right? Otherwise, Julia code is slightly slower. So from the benchmark, it is clear that Julia code is, I don't know, 42 times, 189 times faster than JavaScript or Python. And compare with respect to the C code, you can see Julia code may not be as fast as C code at version 0.6, but very comparable, right? You know, Julia version 06, it was, let's say, 8 or 7 years ago. This is a very recent benchmark from roughly last year. I accessed last year for Julia version 1.0. Now the latest version from Julia is 1.11. Those are the so-called micro benchmarks for common tasks. For example, string parsing, numerical loops, you know, lots of numerical calculations. And here, this is the C code baseline. Yes, my virtual pointer is correct by chance. For C code, this is the unit baseline. And then compare the performance of C code with respect to Julia, Lua, Rust, Go, Fortran, Java. As you can see, Julia code is roughly as fast as C code, sometimes a little bit slower, but for some cases, for those micro benchmark cases, maybe for loop or random number generation, Julia code can be faster than the C code. But by the way, this benchmark does not include the so-called compile time. I will talk about what's the meaning of compilation for Julia. This is unlike, you know, C compilation, GCC, and then you get your source code. Or Fortran, Fortran, you get your source code. Julia has a specific compilation procedure I will cover later. But anyway, Julia code is fast, and you may still have questions in your head. Why Julia code is fast? This is a good question. That's why I have this session. And then, in order to write performant Julia code, you know, at high level, very productive, and also achieve the performance of C code, we need to have a high level understanding about how Julia compilation pipeline works. But no worries, no deep, you know, dive into 0 and 1, you know, like silicon level. I will show you a very high understandable level for Julia compilation pipeline so that you can write performant Julia code. And this is the purpose of this course. Okay, let's go Julia compilation. Yeah, Julia compiler. I think maybe you have experience with C, C++, Fortran, Fortran, I don't know. You have tons of experience with other compilers. Julia compiler is, let's say, different. So Julia does not really compile the code when you define your function. For example, if you define a function, like Alex mentioned this morning, function, let's say hello world, print hello world, and you have a function, but this function is not compiled yet. So basically, Julia takes the advantage of the so-called just-in-time compilation. What does it mean? This means this function is only compiled when this function is called for the very first time. Otherwise, this function is never compiled, like never used. So this is the so-called just-in-time compilation. And later on, I will go through the whole procedure about just-in-time compilation. And after defining a function in Julia, this physical laser pointer has less energy than I. So let's give it up. Let's give it up. So a function is compiled, or the machine code will be generated if it is called with the same argument. Here, I would like to highlight what's the meaning of the same argument. The same argument means not only the number of the arguments, but also the argument types. For example, if this argument is an integer passed to the function, or a double precision number, or I don't know, single precision number, or even a complex number. So the same argument type has two meanings in Julia, unlike C or C++ or Fortran, not only the number of the arguments, but also the type. And otherwise, if different arguments, I mean, either a number of the arguments or the type, the Julia compiler, just in-time compiler, will be triggered to get a new method for this function. This sounds confusing. Yes, that is why we have this very simple but very effective example for you to understand this procedure. So first of all, we have this lovely but very simple function fx equals 2 times x. By the way, you can ignore this star in between because Julia is, let's say, smart. You can get rid of this star, just put fx equals 2x. This works also. And after this function is defined, you will see that you have a function, but with only one method, right? This is understandable as this morning Alex mentioned this mountable dispatch. And then you just define a variable, which is v equals 1.2, very simple. And then you would like to measure the performance for this extremely simple and naive function to get the time. And you can see the calculation is very fast, of course. It takes, let's say, 3 milliseconds. However, if you look at the details, the compilation time for this function takes 99% of the total time. What does it mean? This means after defining the function is not really compiled. And in order to run the function, to measure the time, the entire time is measured, including the compilation time. That is why for this very simple function call, it took 3 milliseconds. But if you call this function again, as you can see, the second call and also the third call, this function call, the function calls take, let's say, almost no time. It finishes instantly. And as you know from this morning session, for Julia, not only you can pass a variable, a single scalar, you can also pass an array into this function, because 2 times an array, let's say a vector, is still valid. But if you change the variable into this array, like this A, you now have a new argument to this function, right? It's no longer a scalar. And then if you call this function again for the very first time, you will see again the so-called just-in-time compilation is triggered. And then the entire compilation time for this function takes again more than 99% of the entire runtime. But the second call and also the following call with different numbers, here A equals 1.2, whatever, and here B equals, I don't know, 12 or whatever numbers, you will see as long as those variables, they belong to the same type, the same array of floating point numbers, to be more precise, double precision numbers, the compilation is not triggered, and the runtime is very fast. As you can see, there are many zeros in front of a valid number. for the runtime. So that is how the Julia compiler works. Of course, you can define a function, let's say, with the same name as f, but with 2 arguments. In this time, we change the number of the arguments, right? Not only 1 argument, but 2 arguments. And then you will have this generic function with 2 methods. Yes? The first method is 2 times x, and this one is, once again, also very simple, x plus y. And then if you put the previous arguments inside to measure to measure the runtime, you will see that the total runtime is slow again because of the compilation time, which takes, again, 99% of the total runtime. This is the so-called the just-in-time compilation. But no worries, if you measure the function execution again, as you can see, the Julia code becomes faster. Why? Because the compiled Julia code has been, let's say, cached in your calculation. And then for the second call, there's no need to compile this code again. And then just the execution like, let's say, normal compiled code. That is where the performance of Julia comes from. And if you use the methods function, you will see now you have 2 methods. One is fxy, one is fx. So this is a so-called mountable dispatch for a function. So not using a single first argument, but using all the arguments to determine which exact method will be dispatched or started for your calculation. So this is the key feature that, please. The question from the audience was, for those benchmarks, the compilation time was included or not? No. Here, yeah, maybe a strongman blocked this. This strongman blocked this this projected slides for you. It's not included, just like normal code. Yeah, that is why I talked about such a long time for the compilation time, because this is really a key concept to understand the performance.
Because I need to compile the code right in order to get the speed when I run for the second time. But if I can get my result from the first run, do I need to run it again to get much higher speed?
Yes, yes. Let me first repeat the question very quickly. The question from on-site participant was, anyway, we need to compile the Julia code, and let's say, is there any benefit, every time to compile this? Because this looks not really needed. It's not an advantage. But actually, there are ways, I will talk about this later, how to remove or get rid of or minimize this so-called compilation time for Julia code. This is a so-called first execution overhead. I will talk about this more, yeah, in the following slides. Let's move on. And so let's continue about how Julia compiler works. This is a very high-level overview. So for the Julia compiler, it has 2 parts. The first part is, of course, the so-called Julia compiler. And then the Julia compiler will process your Julia code and then send your Julia code to the backend. the so-called LLVM backend. And then it is the responsibility of LLVM to produce the so-called machine code for a specific computer. And this computer can be, I don't know, Microsoft Windows with x86 or Linux with ARM architecture, many platforms, many architectures. That is why Julia is possible for many different computers using Windows, macOS, or Linux. And then I'm going to dive into this compilation pipeline very quickly. So first of all, on this side, on the right side, you see a very high-level graph showing you how the Julia source code is processed to generate so-called executable, like C executable or Fortran executable. So basically, there are 4 steps. The first step, corresponding to this step, is to parse your Julia code to generate the so-called abstract syntax trees. Yeah, don't worry if you do not have experience with these ASTs. This is like just doing some analysis of your human readable Julia code to generate something that is easier to be understood by the computer. And then these Julia ASTs will be lowered into the so-called Julia IR, Julia intermediate representation corresponding to this lower stuff. And afterwards, Julia compiler takes no responsibility because everything will be passed to the so-called LLVM and to generate the so-called LLVM IR, the LLVM intermediate representation. And last, the LLVM will generate the executable file, like a normal compiled code for C or C++. Yes, once again, if you want to learn the details, I recommend this paper published in 2018. It is like a milestone for Julia design. So I will go through this procedure quickly because this is a very high-level overview. So the first step is the so-called parse and macro expansion. So if you are typing Julia code like fx equals 2x, just multiply x by 2, it is a string, right? It is a string. Like 1 plus 2, it's a string. It's readable for human. But to make it readable for the computer, you need the so-called parser. And fortunately, the Julia has its own parser, to help the users or developers to go through this procedure. And then after doing this meta pass, you will see that this 1 plus 2 is something like this tree, the so-called abstract syntax tree. This is a core with an operator, which is plus, and with 2 operands, 1 and 2. So very simple. And also you can dump this express to the symbols. This, as you can see here, the output, you have, this is, let's say, text representation of this Julia AST. But anyway, the first step is to do some, analysis of the Julia code to make it more easily understandable for the computers. And also, this morning, Alex talked about macros, right? Macros will also be expanded, to the more computer easily understandable form so that the process can continue. And then this analyzed Julia code will be lowered. Julia is a high-level programming language, right? For the computer to understand this, the code must be lowered. And then the lowered Julia code is, you can use this macro Julia lowered to return the so-called lowered Julia intermediate representation for a method. Here, once again, this function multiply by 2 this function. Here, I define only one method. And for this method, we can put either integer as an input, and then to generate the so-called lowered Julia intermediate representation. And if you look at the code, even though it is called lowered, like a little bit low level, but this is easily understandable by human, right? This is still 2 times x. It's not really very low. And also for, let's say, floating point number, this looks the same. So the key here for this step is Julia IR is lowered, not as very high level original form, and this Julia lowered IR without type specification. The type is still the general type, as you can see here, 2 times x. And currently, there's still no Julia optimization involved yet. As you can see, this circle, Julia optimization, has not been involved yet. But it will be involved because the type of the variable is the key for the performance, right? And then the next step is you can use code typed to visualize this procedure to generate the so-called type inferred Julia IR, the type inferred Julia intermediate representation. Here, there are 2 types of optimization done. The first is the so-called method specification. Method specification means to generate, let's say, computer more understandable method for a specific argument. I will show you concrete example in the next slides. And then to do some type inference. For the type inference, you know, if the compiler knows more about the type, the more efficient machine code will be generated, right? This is straightforward. Here, let's look at the so-called typed Julia IR. This function multiply 2. This is a function multiplied by 2. If the input argument is an integer, here it's 64-bit integer, you will see the real triggered, let's say, typed function is multiplied by integer, right? See this laser pointer is a multiply by an integer by 2. And the return value of this function is integer 62, as you can also see here. This is, let's say, if you are giving an integer to your function. But if you are giving a floating point number, for example, this single precision point number, you will see instead of triggering this multiply integer, this multiply floating point number will be triggered. And the return value is 32. You may have the question, what's the difference? Because a computer, you know, this silicon, can distinguish integer and floating point number very precisely to find out which is the best way to run those calculations by using the silicon, the transistors. And if you instead of giving integers or floating point numbers, if you want to do calculation by complex numbers, yes, I think maybe some of you has experience with C, right? If you are using complex number, it's not really straightforward, right? For C. And for Julia, it's very straightforward. You just use a complex number, put it in, and it just works. Yes, from the user level or high level, this is very simple. But from the lower level, or let's say machine level, as you can see, the generated type inferred Julia code is very different, right? For a complex number, first you get the field for the real part and return the floating point number 64, and then do the multiply and get the field for the imaginary part, and then do the multiplication, and then generate the final complex numbers and so on. This is, let's say, what is really happening for the Julia compiler. As you can see, for us developers, Julia developer using Julia programming language, it's very productive to just write and use those functions. But for the compilers, specific method or those specific lower level statement will be dispatched and executed by the CPU. That is why you get performance. And as you can see, it is very important to let the Julia compiler to recognize the type of those variables correctly. That is why the so-called type stability is the key to the performance of the Julia code. As you can see, for this small part, we have 4 slides, because this is a really key topic for the performance of the Julia. So if a method is type stable, and then the compiler will assign the so-called concrete types. Concrete types means 64-bit integer or 64-bit floating point numbers, or you can think of those concrete types. And then by taking advantage of this concrete types, you will have a performant Julia code. To show you a counter example, here I have a type unstable structure. Maybe this morning you have this question, and Alex also referred to my session this afternoon. So this will be type unstable, but let's assume we have no knowledge about it. We just create a structure, looks nice, and then we create a variable with a nice name, best example, and assign a value to it, which is 3, right? It looks very nice. And then we have a function, also seems quite okay, 2 times this variable, this v variable in this structure. Everything looks great. But if we run this code typed macro to do the analysis of this function, 2 times some variable, you will see instead of showing you 64-bit integer or I don't know, 64-bit floating point numbers, you see any. Any means any, whatever you want. And for human, it's okay, right? But for computer, it is a critical performance issue, because computer does not understand what's the meaning of any. No idea what's the meaning of any. So if we are using Julia to develop the code, there is a very nice macro that you can use called one type. This macro will highlight the problematic part in your code in red, as you can see. For example, type instability will be highlighted in red, as you can see. Any is red, any is red. So for Julia, if you see something that is red in the output, it is not a good signal. For example, there may be syntax error or maybe something like any. Those are not good for the performance. And also, if you look at the details, right? This is base get properties. What's the meaning of get properties? I have no idea. So those are the performance issues, even for doing such a simple calculation, 2 times a variable. That is why in the beginning, when I mentioned 2 times x, maybe you want to sleep. What's going on there? It's nothing, but it's very rich, as you can see. Okay, in order to make this, to fix the problem, we need the so-called type stable statement for this structure. To make it type stable, just put int, double colon, int after this variable name. And then the compiler has the knowledge. Okay, now this variable inside this structure is an integer. And by default for Julia, yeah, if you are using 64-bit, normally 64-bit operating system, it's a 64-bit integer. And then let's go through the process. A good example has a value, again, 3, and then type of this variable, as you can see, it's 64-bit integer, right? It's recognized correctly. Yeah, there's no, everything is very clear. And if we try to look at the code type, which means the type inferred Julia code, you will see instead of those any, you will see exactly integer 64, integer 64, integer 64. And then if you run this macro like I talked a minute ago, a code warn type, you will see that everything is green, right? This is like ampere. If it's green, it's great. If it's red, it's bad. Everything is green. You have correct integer type. You have correct integer type here, and the return value is also correct. This is the value for the return of this function. So everything is correct. So problem is solved. Yes, this is the very last slide for this type stability. You may have the question, why this is type unstable, and why this is type stable only by adding this double dots int. If we compare that, you can think about a structure in Julia like a container, right? This container, but with a dash line, because there's no constraint for this container. And also for this container, it contains something. But what is something? No one knows. The size of this thing is unclear. There's no constraint. So one word, everything is unknown. So in order to make the code running, Julia must specify, okay, everything is any. As you can see, this is not really efficient way to do that. But if you specify this int inside, okay, the compiler knows, okay, this is a structure, it likes a container, and this container contains an integer. Everything is concrete, as you can see, with a solid line, solid boundary. So everything is clear. The compiler, the Julia compiler, LLVM, whatever, can try the best to optimize the Julia code to generate the most performant Julia code. That is why you saw in the beginning the generated or the compiled Julia code has really high performance as C, Fortran, C++, and so on. Much better than Python or JavaScript and so on. Okay, last but not least, the type inferred Julia IR. As you can see, I put it into red. It's not an error. It means it's very important. The type inferred Julia IR will be passed to the LLVM so that LLVM will perform further optimization. You know, Julia is really trying to get the very least point of the performance from the code. I will show you this later. The LLVM will perform further optimization to generate performant code. To get the LLVM, you can use code LLVM. But this macro is, let's say, not really critically important as type inference. Type inference is really key. But anyway, let me show you what is LLVM IR. So here again, this function 2 times x. Let's say if x is an 64-bit integer, here it's 3, and then after doing those high-level process, generate the type inferred Julia code or Julia IR, and then LLVM will optimize the code to generate this instruction, SHL, whatever, 64-bit integer. What's that? We want to do multiplication. Why here is SHL? What's the meaning of this? But if you dive into it, SHL means to do the shift of the bits in the for an integer. So I don't know how many of you are comfortable with bit operation. This is really a little bit low-level operation. So to do a multiplication by 2 is inefficient for integer. What? To do multiplication by 2 is inefficient. Doch, it's inefficient. To do a bit shift is more efficient than do the multiplication at the silicon level. I mean, silicon level means a computer, you know, really those transistors. So that is why the LLVM changed this multiplication by 2 by using this bit shift operator. I'm not going to dive into this into details, but as you can see, yeah, it's getting interesting right now. However, if you want to do floating point operations, let's say 2 times, I don't know, 1.2 or 3.0, and then maybe you are expecting a shift. You know, I talked about bit shift. It's more efficient, right, for integers, everything very close to the silicon. But you will see that there's no shift operator, but you will have this so-called FMUL, which means floating point multiplication. So for floating point numbers, as you can see the differences, really a real multiplication by 2 is executed, returns the product of 2 operands, as you can see here. So that Julia, in the end of the day, will really generate the most suitable code for the silicon, right? As you can see, why Julia has the high performance. And we are still 1 step away from the silicon. And the last step is to generate the so-called native code. This is, you can think of it like the so-called assembly code, you know, really very low to the silicon. And you can take a look or inspect the generated native code by using this macro code native, and then you will get the so-called native code. This is not really useful for normal, let's say, for 90% of the developers. But anyway, if you found it interesting, you can take a look. And the generated native code, as you can see, depends on the processor architecture. For example, the ARM computer, for example, like the Mac, or the x86 computer like this ThinkPad. I will show you some differences. But for this part, you just take a look. It's not really, you know, critically important. So let's say if we are using a Mac, I think some of you are using a Mac with ARM architecture. You know, ARM is a RISC, which means the instruction length is fixed. So here you see they have fixed instruction length, the same length. And here it's the bit shift operator, but for ARM. Okay, but for ARM. If you are using Linux x86 like what I'm using here, you will see that because x86 is CISC is a complex instruction CISC. You will see that the instructions is not the same. Some instructions longer, and here instead of doing a bit shift, here is an x86 instruction, the so-called load effective address, to try to execute this 2 times x more efficiently on x86. You can forget about this low-level instruction, but I just want to show you the key is really the very close to silicon instructions suitable for the CPU will be generated to have the best performance. And let's take a look. If you are using, let's say, the so-called 64-bit integer, and then instead of using this address manipulation instructions and so on, you will trigger this v_add_ss, which is the add scalar single precision floating point number value. Yeah, forget it about the name, but the key is if you are programming Julia from high level, you are writing identical code. Yes, just the 2 times x. But the compiler is really, really able to optimize your code to the silicon value at the transistor instruction level. So that is the key that Julia code is very performant. Yeah, for those, v_add_ss, you can forget it right away. So here is the very summary for the Julia compilation pipeline. As you can see, there are several steps. For example, parse the Julia code, lower the Julia IR, and LLVM IR native code. There are several steps, but the key step that we care about is this one, is this type inferred Julia IR. This is the key. As a Julia developer or developer using Julia for your work, for your research, you must make sure that the type inferred Julia IR is correct without whatever any. Otherwise, the performance will be very, very bad. Okay, I think this is the end of this compilation pipeline. So one key takeaway is to make sure that the Julia type inferred Julia IR is correct without any. And then for your question, this Julia compilation, this is, yes, I fully agree. This is overhead, for the execution. That is why there is the so-called static compilation, which means one is able to get a static executable, like executable you will have after compiling C code or Fortran code. This is called static compilation. Julia just-in-time compiler works, but there is a so-called time to first execution overhead, as you mentioned, and also I think audience, you have all see this overhead to the first execution, and cannot generate self-contained binaries or libraries. This is not really convenient. And there is actually an official ahead of time compiler. Ahead of time compiler means like the normal compilation workflow, a GCC followed by the C source code, and then you have your binary code. This is in active development. And as far as we know, it was announced last year in the Netherlands. And currently, it is still in development, and it's not really included in the official release. But you can have this Julia C, Julia compiler from the development branch to have it or to try about it. But this is from the official Julia development team. But for users, if you really want to release your fantastic Julia code to users or your team members or your colleagues, you can use those Julia packages and then to compile your Julia code statically. So package compiler.jl, precompile tools.jl, and so on. And for this course, the very last part, I will just go through this package compiler.jl very briefly. But for you, this is just a small demo, I think maybe 10 minutes. Feel free to choose or to use whatever Julia package that can help you to generate the static executable. So this package compiler.jl enables static compilation of your entire project to an application like an app. And it just works, right? After compilation, it just works without overhead. This is very great. And also, for example, your colleagues or your team members can use your application without Julia installation, believe it or not. Yes, they can forget about any Julia installation on the system, HPC system or laptop. They can just run your code. And also you can, let's say, make your Julia source code to be a secret. No one is going to, they can do some reverse engineering, of course, but there's no straight way to get your Julia source code. So this is very useful. And to use it, just using a Julia package, like the normal package installation mentioned this morning. And then you will get the so-called app of your Julia source code. So what's the meaning of an app? App is nothing, just a bundle of executables, libraries, the dependencies, everything into a package. And then you can just send this app to your coworkers if they have similar operating systems and CPUs. For example, if they are using Linux or macOS or, I don't know, a similar operating system and CPUs, they can use your code immediately without compilation or, even without installation of Julia. So this is fantastic. So the workflow is also very simple. First, you create a very small Julia project like this. Create a project, and then you can create this hello world like module. Just print a hello world function, and the requirement is here. The return type of this Julia main is a C-type integer. So I think this is understandable for C programmers because C programmer is always starting with int main blah blah blah. So that is why here it's return type is C-type integer. And then the third step and also the very last step is to just compile or to create your application. But during the creation of your application, unlike C or Fortran, if you compile a hello world from C, you will have hello world and C, nothing else. But for this, you will have some, let's say, extra libraries like library LLVM, library LLVM, and so on, and with, let's say, large size, because this is the dependencies. So that is, that is not ideal. So at this stage, the size of the statically compiled Julia package is larger. But the good thing is you can release your Julia code, compiled Julia code, to your colleagues without Julia installation. As you can see here, this is my example. If you type is a Linux command to find out Julia is not installed, right? But nevertheless, you can still run this application without installation of the Julia. This is really nice. And also for your coworkers, they needn't to understand what's going on in your Julia code. Yeah, is this hello world or whatever? Yeah, you can hide the details of your source code. Yes, as I mentioned, there are drawbacks at a current stage. The first drawback is the compilation time. It takes long because the official static compiler from Julia is still in development. And the second point is the size of the generated app is really large because of the dependencies of, I don't know, lib Julia, lib LLVM system dependencies, lib Julia, and so on. So as you can see, in the end of the day, this Hello World application takes 700 megabytes. This is horrible, I would like to say. This is horrible. This is only for Hello World. This is horrible, yeah. Yeah, but you still have other packages that you can use. This is only one option. So I think time's up. And the summary for this part, I hope I convinced you that the Julia code is very fast because of the Julia just-in-time compilation, so that you can combine your productivity and performance together, right? And then we go through this Julia compilation pipeline very briefly by parsing, lowering, and so on. But the key is the type inferred Julia IR. This is the key to the performance. This is the key takeaway. You can forget everything. I'm happy if you forget everything except this one. Type inferred Julia IR, this is the key. And then for Julia optimization, there is a so-called method specification. Yeah, depends on which type of the variable you are passing into the function. Integer, double precision, or complex number, I don't know. And the type inference is the key. You must make sure that the type stable method is generated, right? This is in red. You must make sure that the type is correct to have the performance from the Julia code. And last but not least, it is the static compilation. And there are packages available, but if you really want to use the official ahead of time AOT, ahead of time compiler, you need to wait from the core developers. Yes, after this talk, you can, yeah, unfortunately, you cannot really write performant Julia code because you really need to combine your Julia code, processor architecture, memory architecture, cache architecture, area architecture together to have the real performance, real high performance code. So, and this topic will be covered by Alex tomorrow morning, and Alex will combine Julia code with those hardware, real silicon together, so that to make your Julia code to perform the best, to have the best performance for your work, for your research. And I think that's all from my side for this afternoon. Yes, acknowledgement. Those materials are from Professor Christian Plese, this lecture, high performance computing oder Einführung in Hochleistungsrechnen. And also we would like to thank Marius, Marius for the course materials last year. Yeah, that's all. Yeah, thank you very much. Any questions from the audience? Or you are all convinced? Now you never doubt the performance of Julia. You are all convinced. I believe you. Graphical process unit will be the very last day. We will cover this topic. Yeah.
May I ask a question?
Yes. Yes.
Yes. On slide 20, I believe it was on slide 22, where you showed the two variants of a struct. Yeah, again, exactly here. So I was wondering, if I remember correctly, in this morning, Alex talked about functions and specializations. So that if you have an input parameter without the type being specified, that then Julia, the compiler, creates an instance of that function after the first compilation. But here in this case, I was wondering, is there not a similar thing for structs here? So if I initialize a struct variable with some data with some int field, does that not automatically get like analogously get specialized?
Yes. First, thanks for your question. So if you do not specify, for example, the type information here, maybe you can see my laser pointer here, for this variable inside this structure, the Julia compiler, I'm not sure, maybe in the future, the Julia compiler may be much smarter, but currently, the Julia compiler may not able to identify the type of this variable v clearly, and then just use any, like you have seen here, just use any. It works in terms of computation, but in terms of performance, it doesn't work, right? Simply, it does not work. In terms of performance, you need to specify this field or this field in this structure to be integer or maybe floating point number 64 or whatever, so that the Julia compiler can identify and then assign this to be the correct type to generate the most performant code. So for human being, it always works. It always works, no matter it's any or integer or floating point numbers. It always works. The only difference is the performance.
Okay.
Yeah.
Thank you very much.
Yeah, thank you too. So maybe it's important to specify this, at least currently to specify this if you are using structure. Yes, please. Here is a question from the on-site participant. The question was, if one statically compiles the Julia code and then release this source code to colleagues or team members, is this a requirement for the operating system or CPU also? Yes, there is a requirement. Zumindest one needs similar OS. For example, Linux. It doesn't matter Red Hat Linux or Ubuntu or whatever, but similar OS and also similar CPUs. Because in the end of the day, the instructions, those low-level things will be executed on the CPU or on Linux or Windows. So maybe you need to ask your team members what Windows or Linux or Mac OS are you using, and then you can statically compile and then send your code to your colleague. Yeah, OS and CPU type, those are important. Yes, this is a good question. CPU, for Intel AMD, it doesn't matter. CPU means ARM architecture, like the MacBook from Alex. It's ARM CPU, or x86, like this x86 CPU, or you know, some other CPU. Yeah, for example, you know this HPC from Japan, Fugaku, it's another type of CPU. So if you compile your Julia code statically on your laptop, it will not run on Fugaku. There's no chance, because that's ARM architecture.